Okay. The last time we start a chapter 3. The chapter 3, in my opinion, is super easy. It's basically we start study transcendental functions, que es the function beyond polynomial and rational. We study 2 or 3 functions new, transcendental. And in the next class, you need to take is trigonometry, I suppose. You complete the picture, the most important analytic function and transcendental function. But the concept we discussed, we start discussing what the inverse function. Do you remember that? Yes or no? Inverse. I want to recall inverse function. It's very intuitive idea of the inverse function. Okay, entonces now remember to analyze when the one function is given, and you need to find the inverse function. Remember the notation that we are using is this. This -1 is no exponent. It's totally symbolic way to indicate inverse. This is equivalent to say inverse. Inverse function of what? Of the given. Okay. Step 1 is always determine if my given function is one-to-one or no. Because it is one-to-one, the conclusion is, see, the answer of this question is yes. Does it therefore the inverse function exists? Otherwise, no. See, the answer is no, no inverse function. No inverse. Okay, therefore, the easy way to determine si one function is one-to-one or no is using the horizontal line test. Because normally we are working with a very well-known function, no? Entonces, in the family of the function that we study, the first chapter, we know, for example, the graph of the function, and you apply the horizontal line test. Is crossing only one point? Yes. Cool. The function exists. Okay, this is my first step. My second step is, well, the most important. Okay, determine the equation of this famous inverse function. But the key idea for doing that is you interchange and the original given function x for y. You automatically replace, interchange, swap x and y. Of course, and the given idea, well, we have the inverse, yes, but the inverse is an implicit form. It's not good. In order to express it in explicit, okay, explicit means que y is isolated, like that. Well, you have solved for y. And that's it. Now, step 3 is to make sure that this inverse equation is correct or not. You are doing the composition in the either order of the given function and its inverse. And we are happy, the ordering is not important. Normally, this is the no general case, but in the particular example of the inverse and is the function and its inverse, yes. And when you apply the composition, you get the identity function. Okay, identity function is the function in which y and x is the same. Okay, that means okay, the function is inverse when you put simultaneously, you apply simultaneously on those each other. Cool. Now, finally, no. Fourth step is determine domain and range. Because this is super important, because the definition of the function is not for the equation. Some people believe that you define the function, write the equation. No. You need to write three things. It's equation, domain, and range. These three pieces define perfectly the function. So now you need to remember the domain of the function given is equal the range of the inverse. And the range of the inverse of the function, and we put the function in this left-hand side, is equal to the domain inverse. And this is totally logical, because doing this action, interchange x and y, you interchange domain and range. And step 5 is the most important, is do the graph. Do the graph. Do the graph of both. But, you know, see the graph of the original is like that. The graph of the inverse is symmetric with respect to the line y equal x. This is the identity function. Look. Identity function. Okay. Now the graph look like, I don't know, something like that. Okay, I try to using my best skill in drawing. Okay, now the thing I try to explain here is different. Is interchange x and y. This is the equation for the identity. But the part I highlight in green color. What's this? Do you remember very well this or no? No?
Yes.
Okay, now so let's do in one couple of the example. Okay, bring me new situation. Example 2, because I did example 1 in the other class. Example 2 is easy, super easy. Suppose that the function is given is like that. It's the quadratic function, square function. Nice. Nice. Now, the quadratic function, well, I know very, very well that the quadratic function is the parabola, no? The graph of the quadratic function without transformation, you know, the basic, something like that. This is y equal x squared. And when you apply, of course, you apply the horizontal line test failed. The confirmation is clear that this function is not one-to-one. Therefore, this function have no inverse. And the inverse function does not exist. And we finished the problem. Yeah, we finished the problem. However, normally we need to exist. See, exist, so you enforce restrictions. The mathematicians, in order to, you know, fix the problem, you copy the same equation, but you put restrictions. So you assume, so normally the convention, the agreement or the notation that we use, you put semicolon, x greater than or equal to 0. Okay, does mean that this part, some student asked me, Professor, what the hell is that? Well, this is the hypothetical domain. So domain, que si you don't specification anything, you suppose que it's already a number. But under that condition, of course, do not exist the inverse. But you are doing restriction in the domain. The domain is basically bracket 0, infinity. No? But you assume only the positive numbers. Our parabola then is no full parabola is a half of parabola. Therefore, when you apply the famous horizontal line test pass. So this new function, okay, by the way, have the same equation. However, we have restrictions in the domain. Yes, these have inverse function. Okay, the inverse function now exists. Okay, do you understand this idea or no?
Yes.
Okay, so what is the next step? Find the equation for inverse. Find the equation for inverse, you take the original gets given here, and you replace f of x for y. And this is always possible, because I know very well that y and f of x is the same thing. But f of x is nice, because allows C, C transformation, okay, and y alone is not clear. Entonces you apply this idea, interchange x and y. This is a crucial idea. And you have x equal y squared. Okay, clear. So we found the inverse, but the only problem is that this inverse is expressed in implicit form. And implicit is not clear, never. We need explicit. Explicit is when you isolate the y. Therefore, similar idea, we apply square root both sides, and we have square root x equal y. This is the new y, and this new y is the inverse function. So it's f inverse function equation is square root x. And it's totally expecting. Hello. It's not new. Okay, the inverse function for the square root is a square power, or the inverse function for the square power. It's a square root. But the only confusing part, at least for me, is you put plus and minus here when you apply the square root. No. The answer is no. And the reason why it's not is because don't forget you suppose always at the beginning is only for the positive value. Okay, entonces es, no plus and minus, similar when you solving in quadratic equation, no? You plus and minus, in this case, no. Okay, we finish that. This is the equation. Okay, now this equation, I need to verify it's true or no. In this case, it's obvious it's true, because you pick one number to square 4, and the square root is 2, we come back again. It's obvious, However, I want to prove algebraically using the idea for the composition. Composition F, composition inverse, or inverse composition F. I suppose that we get identity. So in that scenario, okay, the inverse is first. Use substitution, this expression here. Here. Oh, here, that doesn't matter, here. Yeah, so you're right. Square root x, no x, square. X will be this x, identity function. And in other order, we are doing different. We are doing, you take x squared and substitution here. So you replace x for x squared. You have square root x squared. Okay, again is x. So it is expecting. So it's easy. Now, domain of x squared and range of x squared and domain of radical x, que es la inversa, and range radical x, que es la inversa. Well, domain of x squared, remember, I assume at the beginning, que es this. Because you do not put restrictions, entonces no one-to-one, entonces the inverse have no sense, and we cannot continue the problem. To continue the problem, you restricted the domain from this interval, bracket 0, infinity. And this is exactly the range of the inverse. They are connection. This set and this set is the same. And this set and this set is the same. However, looking the square root, you know, the only restriction is you take the expression inside the radical, is just x, ignore the radical for a moment, and you enforce it to be non-negative. So it's a coincidence. It's a coincidence. Not always happen, but it's a coincidence. Another example that I bring, not necessarily the same, but in this case, yes, it's bracket 0, infinity, and here is the same. Bracket. The coincidence is the equal between this and this, or this and this. This and this 100% is coincident. Okay. Now the graph, we predict a little bit. After that, I want to check in Desmos. The graph is, you know, the parabola is something like that. This is x squared. And the inverse function is square root. The square root is a function like that. Okay, we have 2 points in common. We have a point 0, 0, because you square 0 is 0 and you square root 0 is 0. So 0, 0 is coincident, and 1, 1 is also 1, 1 because it's a number raised to the any power or any roots is 1. And don't forget the famous line that represents the identity function, okay, the line y equals x. I only put in the first quadrant because in the third quadrant have no sense because we have no function here. Remember, our domain is only x positive. Just in case, I want to show you in Desmos I did that. Let me try to share Desmos in this example. This is example 2, no? Yeah. Boom. Do you see Desmos, guys?
Yes.
Look, I did that. Look, I put a function. That function is the blue. I put the orange color and the right square root function, the inverse. And this is the famous line, dotted line, identity function. And you see the symmetry in between the graph. Well, I put different points to illustrate the idea, 0, 0, 1, 1, 2, 4, and 4, 2 in the orange. Cool.
Yes.
Super, right? Okay, now I want to bring another example, very, very interesting, because the original function in the number 3 example is rational function. And you know, in rational function, we have horizontal asymptote, vertical asymptote, and it's obvious. See, when you find the inverse function, you interchange x and y. For example, the vertical asymptote and the original given function is now the horizontal asymptote and the inverse. And likewise, the horizontal asymptote and the given function is now the vertical asymptote and the inverse function. Because it's obvious, no? Because you interchange x and y. The thing is happening, and x and the original is now happening in the y and the inverse function. Then let me see example 3. Example 3, let me erase the board and share the screen for the board. Okay, cool. Do you see? Do you see or not?
Yes.
Okay. Example 3 is, look, is, I don't want to complicate too much this. But this is important because you need to know, and the teacher explained to you trigonometric. In one moment, need to talking about inverse trigonometric function, and it's the same idea. Therefore, normally the trigonometric function is not one-to-one, so you need to make restrictions for the domain to be possible, so the inverse function exists. By the way, you need to take trigonometry next semester.
Yes.
Take advantage if you want, no? And take it with me. It's in the morning, but it's in person. It's Tuesday. Let me see, Tuesday and Thursday, at the same time, guys. 11:15 a.m. Okay, 16 week. Okay, so you like with me, no? Okay, so now suppose this example that the function is 1 over x plus 1. Oh, it's easy. It's rational function. Okay. The polynomial in the top degree is 0 because it's just a number, constant. And the polynomial in the bottom degree is 1, linear. Okay, you are familiar with this. Okay, so now, I need to determine if it's one-to-one. Okay, to analyze one-to-one, I always recommend to the graph. But the graph is similar, in my opinion, similar to the function 1 over x, no? You are familiar. The function 1 over x, I know very well, first chapter. Okay, the graph look like that. It's obvious that the domain of this function I take like a reference to understand my function is all real number except 0 because in 0 to be undefined. That is the reason that we have here a vertical asymptote at 0. Also, we have the horizontal asymptote at y0. It's obvious because degree is 0, degree is 1, so you remember the analysis of the degree. When the degree at the bottom is bigger than, entonces es special horizontal asymptote. But this is the graph of this. But the graph of this is similar because they are family. And what is the transformation? You see some transformation. You see that function. Suppose I call this F. I call this G. Different name because it's different function. But the connection in between this, so G is Fx plus 1. It's the only thing. You replace x for x plus 1. And this is horizontal shift. Horizontal shift 1 unit to the left, no? The left. So my graph look like that. Similar. So you move the graph 1 unit to the left. Therefore, the only guy can change is the vertical asymptote that now is not in 0 and -1. Okay, this is vertical asymptote at x equal -1. And the rest approximately stay the same. Could change the number, change the y and the z, but this is not important now. And the horizontal obviously stay the same because the transformation that we are doing moving the graph horizontally. Therefore, the horizontal line stay the same. It's obvious. But it's not important. The important is now the analysis of the horizontal line test. What do you think? Pass or fail?
Pass.
Pass. Es obvio que pass. Therefore, we justify clear justification que es 1 to 1. Therefore, the inverse of this exists. Okay, entonces en the step 2, my goal is find G inverse equation. Okay. I take the original. You replace the function notation for y. And so far, we are doing nothing. Now, this is a crucial moment in which you interchange x and y. Crucial moment. Okay, now, x is equal 1 over y plus 1. Boom. And this is the inverse, but the problem is que it's not explicit, so it's not clear. Okay, so I try to do my best in order to isolate the y. Why not you apply cross multiplication, x times y plus 1 equal 1. You distribute here, xy plus x equal 1. You, for example, move x to the other side, 1 minus x, and finally divided by x. Y alone is 1 minus x over x. And this is the equation for inverse equation. And it's no f, it's g, is the name of the original. So g inverse function is 1 minus x over x. Okay. Well. Do you understand very well the algebra part?
Yes.
Okay, if you want to visualize a little bit this graph, one way is, you split this common denominator and you have 1 over x minus 1. Basically, it's the same idea of this. Look, this is the graph of the 1 over x. But the only thing that we are doing in this graph is subtracting 1. And subtracting 1, is like a G, no, it's G, it's F, That's f. This f minus 1. So basically, this -1, -1 represent the vertical shift 1 unit down. Entonces, si es 1 unit down, the only thing que change in this graph, in this graph, is the horizontal asymptote. But the horizontal asymptote now is not a y0, is a -1. 1, -1 here. This is my new horizontal asymptote at y equal -1. Where I come from this -1, this -1. And the graph, you know, there's no 100%. And the vertical, no, the vertical stays the same. The vertical asymptote stays the same as 0 because the motion in this case was vertical down. Now my graph look like a little bit like that. Of course, change the x intercept, the y intercept, maybe, but it's not important for me. I don't like this. Okay. After you see clear and Desmos this idea. Everyone follow me?
Yes.
Now the next step is the checking, the double checking of the composition. The F composition, F inverse, and F inverse composition. To see if actually undoes each other and give me the identity function. No? Suppose you take the inverse, get this. I don't know why I always write F. Actually, in this problem is no F, it's G. G. So the thing we are doing is G composition G inverse and G inverse composition G. Let's do in the first case this. So G inverse is my innermost function and use substitution where? In the region here. So you replace 1 over 1 minus x over x plus 1. Do you understand the thing I'm doing or no?
Yes.
Okay. Okay, then to see more clear, I apply some algebra here. You, for example, find the least common denominator, is x. Here, because we have 1 over 1 in my mind. There's x, this is 1 minus x plus x. Oh, fantastic. This x is cancelled and stay 1 over x, reciprocal is x. Good, identity function. Now let's do it in different order. We are doing, you replace this here. Replace in 2 places, in x here and in x here. Because we have 2x, no? But you're right. 1 minus 1 over x plus 1 divided by 1 over x plus 1. Let me see if I did well or no. Yeah, x plus 1. So you replace x for the entire g is 1 plus x. Okay, algebra now. The least common denominator in the top is x plus 1. We have x plus 1 minus 1. 1 over x plus 1. This one is cancelled, guys. And we have now x over x plus 1 divided by 1 over x plus 1. Division to fraction, complex fraction. You complete the first, exactly the same, and you multiplication, flip it up. This is cancel and stay identity again. Cool?
Yes.
Okay, now domain, and range of both functions. Es obvio que the domain of my original G function is all real number except -1, que es the value que es asymptote. Yes or no? You take. Look, you take denominator. That's all we are doing. Analysis of the rational function domain. You take the cube polynomial and force it to be 0. Es -1. So my domain is all real number except -1. It's the only bad guy que to be undefined the function. Entonces, you write like that. Either way, guy, is x such that x no -1. And this is exactly the same, the range, identical expression range of the inverse. But the only detail difference is that you open the curly bracket like that. You put the y because we are talking about range. And range is y value. And you copy exactly the same expression. Now the range of G, and now the domain of inverse. Remember, domain of this is equal to the range of this, and domain of this is equal to the range of this, but I have no idea what is the domain of G inverse, but I am looking this expression. It's easy. The expression for the G inverse is 1 minus x over x. If you want to determine the domain of this, it's easy. You take denominator and denominator non-zero. Therefore, the domain is x such that x non-zero, and the range of G is y such that y non-zero. Guys, it's obvious. Okay, I make a decision, right? Domain and range are set of the x or y value que satisfy the function, no? Okay, is defined. Si it's undefined, no. So you write like that, oh, in the test, normally, I ask you in interval notation. Interval notation is the same. O sea, the only thing you need to know is this is equivalent to say from -infinity, -1, parenthesis, union, -1, infinity. So basically, in -1, we have a hole in one dimension, no? Okay, now the graph is a little bit complicated. When I try to do here, but no roughly sketch. You want to see more clear and detailed and simultaneously both together, we use Desmos. So Desmos. Easy. Do you see Desmos?
I still see the whiteboard.
Whiteboard, still whiteboard.
Yeah.
Okay, let me switch again. Now?
I still see whiteboard.
Because sometimes happen, I need to stop sharing Now, do it again. Now?
Yeah, I see Desmos.
Okay, example 3. Example 3 is, wow, look like horrible. But don't worry too much. Let's do it step by step. This is the original function. Let me delete everything. Delete, 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 delete. Okay. Delete and delete. Delete any point. I plot the original function, and this is expecting. Okay. Okay. Is the reciprocal function, but the only problem now is the vertical asymptote is at x equal -1 and the horizontal is in y0. Let me flash it. Vertical asymptote, horizontal asymptote. Okay, I copy here different points. I copy, let me see, 0,1. Oh yeah, 0,1 represent the y-intercept for this function. So it's easy. You plug in 0, you replace x for 0, and 0 plus 1 is 1, 1 divided by 1 is 1. This is the y-intercept. Okay, now it's clear, I suppose. Now the inverse function, I determine algebraically, guess something like that. And this has horizontal at y equal -1. And vertical at x equals 0. And very, do you see how? Okay, let me try to match it by couple to understand. Delete this and delete this. Okay, I have in the original red color this vertical. Do you see how flashing? It's -1. Now in the inverse function, it's the same value, it's -1 per y. Okay, that vertical become like a horizontal in the inverse function. Likewise, let me putting off this. Y equals 0, okay, the horizontal and the red now become like x equals 0, okay, vertical and the purple color get inverse. Let me replace everything. Why not? Let me try to show you the line y equal x gets the identity function, and you see how the red curve and the purple color curve are symmetric with respect to the line y equal x. Let me complement that with the different point. For example, this point. This is super important, because we're using this idea to do easy the graph. Suppose that I have in my hand the intersecting and the red color gets 0,1, and when you switch interchange x and y, this y-intercept become like an x-intercept, it's 1,0, and the purple color. So because it's easy to understand, you interchange x and y. In the first scenario, x is 0, y is 1. Now you interchange, you swap. Now x is 1 and y. Entonces y is 0. Conclusion, and so the y-intercept become like an x-intercept and inverse. Likewise, arbitrary point, okay, is 1,5, 1/2. And inverse would be 0.5, 1. I have another -2, or -1. And the red one, okay, is and the blue and the red one, sorry, and the purple color is -1, -2. Do you see the symmetry of the point? And the symmetry, yes. Okay, and the symmetry of the asymptote?
Yes.
So we take advantage of this fact to understand more complicated functions. Okay. Okay. Let me check it attendance. Okay, cool. Okay, I see your names. I copy the piece of paper. Okay, cool. Let's come back to the whiteboard because I want to introduce new idea. Okay, whiteboard. Do you see my whiteboard?
Yes.
Okay, cool. Now we study the exponential function. This is my first transcendental function that we study. Exponential. It's a family of the function. And this is extremely important. And you need to understand very well the difference between exponential and the other function that we study, polynomial, rational, completely different. Let me try to start for the definition. We study different elementary examples. And you see after, you see the property for these functions. And you see another, you know, it's very, very contra-intuitive idea, the exponential function. I suppose you hear in some moment in your life, the population of our planet increasing exponentially. And entonces you understand that this increasing too fast. Actually, it's not true. Or you hear that the propagation for the coronavirus increasing exponentially. This is to indicate it's too fast, but actually it's not exponential. I want to explain why in your moment. I promise we finish this chapter with the application of this. Okay, you need to understand very well the theoretical part. Let's do in several elementary practice example, and after we finish in the application, get the word problems. Okay, so now what definition? Definition is it's a function. Can you define like that? A to the x. And who is A? A is the base. In general, is real number. But never negative. By definition, guy. So let me write different, antonym. But A is always positive. And very important, and. Let me highlight positive. It's important, this word, positive. And no zero. And no one. Okay, let me try to explain clearly this idea. For example, 2 to the x is good. Square root 2x to the x is good. It's a real number, maybe rational or irrational. But negative 2 raised to the x, no exponential. So it's totally illegal by definition, and the base is negative. Okay? And 1 and 0, there's no illegal, but it's a stupid, it's trivial example, because 0 raised to the any power is always 0. And 1 raised to the any power is always 1. This is trivial. Trivial value, 0 and 1. And negative, never, illegal. And positive, yes. Be rational, maybe fraction. Of this, nice. Of this, nice. Okay, it's perfect example for the exponential function. Do you understand the definition?
Yes.
Let's see one elementary example. Okay. Oh, no. Let me finish the definition with the one complementary idea. So we have two scenarios. Bueno, professor, I understand. However, one part is confusing. Let me try to clarify this. Look, you say que the value of the base, que es A, suppose this is my Orion number line. Okay, here is 0. This is 1. And this is Orion number negative no. No, you say no, negative no. Definitely no. But you have two intervals here. And between 0 and 1. So it's the base and between 0 and 1. No 0 is illegal. No 1 is illegal. Not illegal, it's trivial. And A greater than 1 is that piece. Okay, cool. The reason I divide this is because we have two family of the exponential. This in which the base is greater than 1 is increasing the exponential. Increasing the exponential. Okay, some book called Exponential Growth. Que es sinónimo to say increasing. Entonces now, typical phenomenon or events like a pandemic or something, no? We can simulate, but no, actually, no exponential. Like exponential growth. Okay? However, this case less than is decreasing. I want to prove in your moment. Decreasing exponential because it's going down. No negative, pero it's decreasing. Que es normally some book call it decay. Exponential decay. Exponential decay is the typical name. Exponential decay. For example, if you want to simulate the cooling process, for example, one object, one pizza is very, very hot. And this is to the 400 Fahrenheit degree. And the temperature you put in the room with the air conditioner, the temperature is going down. And this mathematical law is exponential decay. And the reason it's decay is because the base is a number. For example, you see this example, okay? I put it here. This is 2/3. 2/3 is in decimal 0.6 repeated. It's less than 1. Therefore, this exponential is decay. However, 3/2 is 1.5. And 1.5 is greater than 1. This exponential is growth. Exponential is going up. And this is going down. Okay. I want to discuss in the detail how going down and what is the boundary, but it's not important now. You understand very well definition? Two kinds of exponential we have. Growth and decay. Okay, entonces study at least one example, professor. Example 1. Example 1 is f of x equal to, it's easy to understand, when the base is 2. We can predict si the base, que es a, is 2. Obviously, this is exponential growth. This function is increasing. Okay, entonces, in order to study in detail, I propose you do the table like that. Put x value, y equal to the x, and here we have a point, x comma y. to plot the graph. Okay, so I suppose that we have no restrictions in the domain. I don't know. After we investigate this, 0, 1, 2, 3, 4, 5. But no 3, 5, 3, 4, 5. Let me investigate the negative part, negative 1, negative 2. It's good. Negative 2. And you plug in it. 2 to the 0. 2 to the 0 is 1. Any number or expression. Raised to the 0, 1 is 1. 0 number is 1. And the point is 0, 1. Wow. This is any number, regardless. What is the base? It's not important the base. It's equal 1. This point is universal point. Universal point for any exponential functions is 0, 1. It's a y in a set. It doesn't matter que es 3 to the x, 4 to the x, 1/2 to the x, 3/4 over x. When you raise to the 0 power 0, 0, 0, the answer is 1, and this is a universal point. And in the test, one important question is, do the graph of the exponential. Now you see that 1 point is always 0, 1. And 1 is easy. It's y equal 2 to the 1 power que 2. Now the point is 1, 2. Well, 1, 2 because the base is 2. In other scenario que the base is not 2, is 1, 8 in general. Makes sense, right?
Yes.
This is the complementary point to do the graph of the exponential. Y to x equal to is 2 to the second power, que es 4. Entonces es 4. Es 2, 4. Okay, good. Suppose que x equal 3 is 2 to the third power is 8. Entonces es easy to understand. It's 4. Let's start negative 1. Y equal 2 raised to the negative 1. You need to remember que negative exponent means reciprocal. Entonces es negative 1, 1/2. Okay, in general, for any base que no necesariamente es 2, es 8, es negative 1, 1 over 8. Entonces this point, and this point together is enough to understand a little bit better the exponential function. And negative 2 is y equal 2 to the negative 2 is 1 over 2 to the second power of 4, 1/4. Is negative 2, 1 over 4. Okay, now let's take in this order pair. I plot that in the rectangular coordinate system. I see our first graph of the one exponential function. By the way, it's exponential growth. Let me try to find exponential. Do you see Desmos?
Yes.
Exponential. Oh. Wow. I put a lot of point. Look. A lot of point is, look. In the positive part, I put the green color, no? 0, 1 is the universal point. 1, 2 because the base is 2. 2, 4. 3, 8. Yeah, I don't know if I put one more or not. No, but the next is 4, 16, no? Duplicate. Yeah, look at that, 4, 16. Do you see the exponential growth increasing too fast? Now, in the negative part, well, negative part is negative 1, 1/2, que es 0.5. negative 2,0.25, que es 1/4. Negative 3 es negative 3,1/8, is 0.125, and so on. And you see how decreasing, but it's asymptotically approached to the axis, x-axis, but never touch. That means that at least this exponential that we study now have the horizontal asymptote at y equals 0. Cool. Do you see that?
Yeah.
Now, let's come back to the whiteboard. Do you see the whiteboard?
Yes.
Let me try to summarize in this part the most important property that you need to know for the exponential, for the family of the exponential function. Suppose the first property, domain. Let me call property of exponential. But not all exponential. Only f of x equal a to the x power, and a is greater than 1. Okay, slow down. So now domain, no restriction. Domain, remember the supposition always we are doing in college algebra is you suppose that the domain is all real number except the restriction, and you have restriction when you have fractions or a square root. In this case, no fraction, no square root, therefore domain is all real number. No problem. It's nice function. Okay, accept positive, negative, fraction, any number. However, the range that the y value offer, the function is always positive. You see in the graph cover first quadrant and second quadrant, never third quadrant and fourth quadrant. No. The graph of the exponential is always give me positive. When you raise 2 to the any number, the answer is always positive. And not 0, because it's asymptotically. Therefore, the range is from 0, but not touch 0 to infinity. Do you see this idea? The graph is like that. Asymptotic. Never cross or touch 0. This is the horizontal asymptote. And you see that the y value cover only positive part and never negative part. No negative part. Okay, now the function is increasing. Remember the roller coaster car can travel from left to right, and the curve is going up, goes up. Therefore, it's increasing function. This is when the base is less than 1. And this interval. The base is in between these different situations happening. I want to study after that. Okay, number 4 is important, is neither function, no symmetric. Fortunately, the positive part behave completely different to the negative part. Not even nor odd, and neither, actually. Number 5, we have always, anytime, horizontal asymptote. Horizontal asymptote. Bueno, add y equals 0 in this example because we have no transformation It's basic exponential. After I want to discuss in some example with the transformation, and you see que no necessarily is always zero, but in this case, zero. So the basic is zero. And we have typical points. Typical point. Typical points. Que es, en plural, the universal. It's important. And 1,8 and negative 1, reciprocal. Entonces, using this idea, we can do every example of the exponential. Suppose, no. This is not formal example. This is complementary. The example one. Suppose que en el test I complicate your life. I put do the graph of the function y equal 5 to x. Bueno, okay, professor, it's easy. I know. This is the x-axis. This is the y-axis. I plot the universal point. Boom. This is 0,1. This guy. I plot another point is 1,5. 1,5, 2, 3, 4, 5. This is 1,5. And the negative part, negative 1, for example, is the reciprocal, is 1/5. So 1/5, my imagination is you split the segment between 0 and 1 and 5 parts. Suppose it's this. And this point is the point negative 1,1/5. Okay, now I'm extending a little bit this axis. I do the graph like that. I know very well that this exponential approaches but never touch asymptotically the x-axis. And this is the graph of the function y equal 5 to x. This is easy, right? For any base, you are doing exactly the same. Don't forget the 3 point and don't forget the horizontal. And we have no vertical. And the exponential, no, never we have vertical, only horizontal. Horizontal at y equals 0. It's coincident with the x-axis. Is it clear?
Yes.
And what about the end behavior? Well, end behavior, normally the end behavior, when you do the end behavior, remember end behavior is the y value when the x approaches to infinity positive or when the x approaches to negative infinity. Okay, in the scenario of the polynomial and rational function, one maybe is like that or like that or like that, no? Okay, in this case, you write, for example, you put right up and left down or left up. In this case, obvious, case right up because there's the part, it's increasing. And left is no down, it's just 0, approaching to 0. Okay, it's completely different to the polynomial or rational. In this case, no, stays constant, stay constant. And approaches asymptotically to the line y equals 0. And the other hands is the right is yes, it's going up totally. Okay. Do you understand this or no?
Yes.
Okay. Let's move it on to another example to understand everything in detail. This example bring me new situation. This is an official example 2. In the example 2, the function is called g, is equal 1/2 raised to the x power. Well, I have no idea. However, I want to investigate, no? To investigate, we are doing similar situation. We're doing the table. To the x value, you put a y value, is 1/2 to the x power, and you put the x comma y order pair to plot that. Okay, cool. Entonces 0, we apply the same point, 1, 2, -1 and -2. And 0, bueno, es 1/2 raised to the 0 power, que always is 1, you know that. Entonces 0, 1, again, universal point. So to understand this, the universal point, you have a family, for example, of the exponential passing through the point 0, 1. Family, but always passing through the famous point 0, 1. Any exponential function is a family of the exponential function, maybe decay or growth exponential, but passing through the famous point universal case 0, 1. 0, 1 is universal, and by the way, it's a y-intercept. And 1 is y equal 1/2 raised to the 1 power is just 1/2. It's 1/2. Entonces the point is the point 1, 1/2. By the way, matching perfectly with the idea with the 1, a, because our base is 1/2. Oh, you say, professor, que when the base is less than 1, it's exponential decay. Okay, let me try to understand what is that. Decay is synonymous to decreasing, you say. Okay, in the graphic I can see. And 2 is 1/2 raised to the second power. And this is 1 squared is 1 and 2 squared is 4. And the point would be 2, 1/4. Nice. Now -1. 1/2 raised to the -1. Wow, this is confusing, very, very confusing, because it's a fraction, you know, it's a fraction raised to the -1. Yeah, I know that -1 is reciprocal, and you flip it like that, 2/1, right? And divided by 1 is nothing, entonces it's just 2. Flip it, right? And the point is -1, 2. And this matching, in my opinion, this idea is -1, 1/a. A is, in our example, 1/2. And the reciprocal of 1/2 is, you flip it, that is 2/1, is 2. And finally, -2. So 1/2 raised to the -2 is reciprocal. Reciprocal is 2/1 because it's negative exponent, but you square. Si square is 2 to the second power is 4. And 1 to the second power is 1. Entonces it's just 4, and this is -2, 4. I need to understand much better when the base is the less than 1. Well, one way to understand this is, look, I take the function again. However, in my mind, I know very well that 1/2 is equivalent to, say, 2 to the -1. And you replace, no 1/2 anymore. You put 2 raised to the -1 raised to the x, double exponent. And double exponent, you know the rule, multiplication, 2 to the -x. Wow. And we compare the function that we studied last time, example 1, that was f of x equal to 2 to the x. Now g, when the base is reciprocal, appear having a -1 in this point, and it's clear for me. Now I need to understand what is the meaning of this negative. Okay, I know very well when we study transformation, when you replace x for -x, we have reflection. Reflection about y-axis. Entonces now, si I do the graph of the original example number 1, que es this, I discover that the graph look like that. This is the famous universal point, 0,1. Suppose que this guy is 1,2. And suppose que this guy is -1,5. This is the graph of the 2 to the x, that one. Now, how look like the graph of the minus? A reflection. And reflection is, let me try to do my best, is symmetric, but in this way. For example, the point 0,1 stay, que es a common universal. However, n1 is this. We have 1/2. This point is 1,1/2. Look at that. And in -1, just this. We have -1,2. Just this. -1. And this new exponential, que es purple color, es obvio que es decay. It's going down, decreasing function. This is the graph que corresponde with the 1/2 raised to the x power, que es equivalent to the -x. Okay, entonces don't be scared when you see in the test fractions or when you see negative exponent, because negative exponent is reciprocal, no? Okay. Any questions so far? Let me show you in Desmos the graphic of the 1/2 raised to the x power. You see Desmos?
Yes.
Let me try. Oh, this is only example 1. Example 2. Look at that. Example 2 is 1/2 raised to the x power. You see in red color. You see it's perfect symmetric with respect to the y-axis. It's just reflection. Because this is equivalent to, say, negative exponent. Okay, you see the same value. You see the distance is the same. And touch here in the famous universal point is 0,1. Okay, cool.
Yes.
Let me bring 2 examples to complicate a little bit your life. Que incluyen transformations. Entonces we study in detail, and we, for example, do finally the graph. Suppose, wait a second. Okay. Do you see whiteboard or not yet?
I can see it.
No, you see? Yes?
Yes.
Okay. Sometimes happen it's complicated to get the share screen sometimes, no? Suppose this example, look at that. This example is example 3 is y or f of x. Let me call it a different name. H of x equal to the x plus 1 minus 4. Okay, in this case, I see we have transformation. My question is, what is the base? What value is the base?
2.
2. Very important to understand that the exponential function is, for example, 2 to the x, 3 to the x, versus the polynomial function que es, x squared. So in the polynomial, the variable is in the base and the exponent is fixed. Okay, and now in the exponential, no, the base is fixed number and exponential is changed. That means that this function increasing faster than this. That is a reason in the popular phrase that the population increasing exponential, but this is not true. I want to explain you more why it's not true. Okay, so the base is too clear. Now you see two transformations, yes or no? Do you see two transformations?
Yes.
Which one?
The -4, and then on the exponent, the +1.
And the exponent plus 1. What kind of transformation is -4? What kind? What kind of the 4 transformation that you very well know? Vertical shift, horizontal shift.
Horizontal shift?
Horizontal shift, -4 is horizontal or vertical?
No, sorry, it's a vertical down.
It's a vertical down. Very well. Vertical shift down 4 units. Everyone is clear in this idea? And +1, so basically is equivalent to say another function, so another function is 2 to the x, and when you are doing this transformation, -4, but no, sorry, no inside the parentheses, outside the parentheses. It's 2 to the x -4. This is vertical shift 4 units down. And another exponent 1 is horizontal shift, yes or no?
Yes.
And horizontal, we have only 2 directions, right or left? And what direction you believe?
Left.
Left, because of positive. Left 1 unit. Okay, cool. Now, one more, we can do that. When we can do that, for example, in order to do the graph, okay, we can do the table, but no, I do not recommend the table. I recommend, for example, doing the y-intercept. Doing the x-intercept. It's a typical point, doing the horizontal ast. Okay. And y-intercept is the same formula that you know very, very well. You evaluate the function and 0. Okay, it's the formula. And the function n0 is 0, 2, 0 plus 1, -4, no? Is 2 minus 4 is -2. Okay, that's the famous point is at the point 0, -2. You plot this point. Okay, now I'm going to find the x-intercept. You know the formula. The formula is h in x equal to 0. So we have 2x plus 1 -4. Wow. And you need to solve this equation. And we get inside in the field of the exponential equation. Okay, I promise we study in detail this chapter. Every day we are solving this kind of equation. It's non-linear. Okay, you are familiar. It's not quadratic, no. It's a new equation we will study now, exponential equation, when the unknown x is in the exponent part. But this is easy in this case because, let me write, is 2x plus 1 minus 4 equals 0. You isolate the exponential part. You move 4 to the other side. And you try, this is the central idea, you try to express both sides using common base. Sometimes it's possible, sometimes no. And let's see what happens when there is no. But in this case, yes, it's easy because it's my first example, no? So now you manipulate and you go before no like a 4, like a 2 to the second. Wow, nice. See, the base is the same and the exponential is the same. So if the exponential equal another exponential and the base is the same, the conclusion is the exponent is the same. Because this function is one-to-one function. Yeah, I forgot to say that. The exponential function is one-to-one. It's obvious. Because look like that. Depending on its growth or like that. And when you apply the famous horizontal line test, pass. Always pass. So the exponential function is one-to-one. Now, wow, since one-to-one, the exponential function has inverse function that we study after, maybe today. No. Okay, so now you solve for x. Oh, nice. And the answer is 2 minus 1 is 1, x equals 1. And the famous point is the point 1, 0. 1, 0 is I forgot, we are doing the x intercept. This is this. And the horizontal asymptote is, remember the horizontal is when the x approaches to positive infinity or when the x approaches to negative infinity. I know very well when the x approaches to infinity positive and the original function. Let's come back to here. In order to find horizontal asymptote, remember horizontal is like an end behavior. But the problem que the habit que we have in the rational function, the rational is special. In the rational function, the behavior in positive infinity and negative infinity is the same. But in this case, no, not necessarily the same. And the horizontal is when the x approaches to positive infinity, it's obvious that y approaches to positive infinity. Because you put 2 infinity plus 1 minus 4. Infinity plus 1 is obvious as infinity because 1 is totally negligible and 2 to the infinity is infinity. However, when approaching to negative infinity, we have different situations. We have 2 minus infinity plus 1 minus 4. Minus infinity plus 1, 1 is negligible. And this is 1 over infinity. And you see in the decay part, okay, when this negative infinity approaches to 0. So 2, I discovered that 2 to the negative infinity is approaching to 0. Therefore, the y value for the our function approaches to negative 4. And this is our famous horizontal asymptote. Do you understand the last part? That part you understand very well or no?
Not very well.
No, ask me. Ask me. Okay, I need to understand end behavior. End behavior is when the x approaches to positive infinity or negative infinity. I suppose that it's super clear that part. When the x is a huge number, million, trillion, the exponential increasing too fast. Entonces, y approaches to positive infinity. However, Different situations happen in this case when the approach to negative infinity. Because approach to negative infinity is a huge number per negative. And to the minus infinity approach to zero. How do you know that? Because the exponential is asymptotically in this direction, no? And you see negative infinity is in this direction, and the y value approaching to zero. See that part approaching to zero, that part is gone, and the entire function approaching to negative. More clear now?
Yes.
Cool. After you see clear in the decimals. This is the beauty. You can verify everything you want. Graphical. Look, this is this. Oh, yes. This is no. This is yes. Okay, look at that. This is my, oh, sorry. I don't share, no? Exponential. You see? No, whiteboard, no? Do you see?
I can see decimals.
Good. That's exactly what I want to illustrate. Look, this is my curve. Look at that. This is my curve, my exponential. You see that the base is 2. We have 2 transformation. -4 is horizontal shift, 4 units down. Therefore, the classical horizontal asymptote that we have in any exponential function is at y equals 0. Now it's at y equals 4. And you see very, very clear the end behavior, how our curve, purple color, approaches to -4 asymptotically. Guys, I promise I never touch. Look at that, asymptotically. Okay? And exactly we discover the x in a set and the y in a set. The y in a set was 0, -2, that point. And the x in a set was the point 1, 0. So not always is the classical 0,1 actually the basic exponential function without transformation. The y in a set is 0,1 universal point, and we have no known x in a set because the graph is asymptotic and never touch. In this specific particular example, well, yes, we have both because the curve is going down and touch the x-axis. We have x in a set and we have y in a set. And of course, the horizontal asymptote change to -4. Okay, by the way, guys, it's the number that you transform it vertical shift down, the -4. Because the behavior, when you go to the negative infinity, look, negative infinity is a huge number, -24, -26. You see how the exponential approaches to -4. That means that value can represent 2 raised to the x plus 1 when the x approaches to negative infinity is 0. It's completely negligible. Cool? Do you understand very well this example 3?
Yes.
Okay, let me try another example. Example 4. You see whiteboard?
Yes.
And you help me a little bit with example 4 because you, little by little, you go inside this exponential function. Example 4 is the function y equal 1/2 x plus 4 minus 4 again. Wow. Okay, what is the base in this case?
1/2.
Exactly. The answer is 1/2. Okay, entonces si I want to classify this exponential is a growth exponential or decay exponential.
Decay.
How do you know?
It's less than 1.
Exactly, because the base, que es 1/2, is less than 1. Okay, now let's do in the idea, find the y in a set, find the x in a set. You can do the table if you want, but no, more practice is find y in a set, x in a set, horizontal asymptote, of course, and we use decimal, no? Finally. The y in a set, you know, very, very, very well, que es the function evaluated en 0. Es the formula que you are familiar. Entonces we have no function notation, but okay, I want to call. This is the function f. I'm plugging in n0. O sea, es 1/2 raised to the 0 plus 4 minus 4, something like that. Well, this is just arithmetic part, easy. 0 plus 4 is 4. Minus 4, minus, no plus, minus. And 1/2 raised to the 4th power is 1 to the 4th power, get 1, and 2 to the 4th power, get 16, minus 4. Now subtraction is negative. 4 is negative. Is negative what? Is negative, find the least common denominator, get 16. This is the only number that we have in the denominator. You suppose 1 here. This is 1 minus 64, no? Because where I come from 64? 16 times 4. It's minus 63 over 16. Okay, this is my famous point, is the point 0, comma, minus 63, 60. Okay, in decimal. Let me try to see in decimal, because decimals give me the, yeah, in decimals. Decimal 63 over 16 is 3.9375. Equivalent to say 0, comma, minus 3.9375. After you see in decimals. Okay, and what about x in a set? There's a function equal to 0. And one more time, we have the famous exponential equation. I promise que we practice in few seconds. Okay, you declare y0. And my goal now is isolate the x. And we found, wow, exponential equation. It's an equation that contains the unknown and the exponent part. Okay, no problem. I try to do my best. My best is 1/2 raised to the x plus 4. You isolate the exponential. And you try to do your best. Sometimes it's impossible, sometimes it's possible. In this case, que es elementary example, es possible. Express it using common base. Entonces, the common base, in my opinion, es 2. Bueno, professor, es 2 here, pero it's 1/2. Pero I know que 1/2 you can represent like a 2 to the minus 1 equal to the second power. Now, you apply the rule of the exponent. When you have different level of the exponent, you multiplication. Entonces, 2 minus x plus 4 equal to the second power. Entonces, again, see, if you have two exponential functions, and the base is the same base, is because the exponent is the same. Entonces, minus, paréntesis, x plus 4 equal to. And magically, this is magic, guys. You convert exponential equation in linear equation. And the base is gone. Okay, yeah, distribute the property is minus x minus 4 equal to minus x is equal to plus 4 minus x is equal to 6. Therefore, x is equal to minus 6. And the point is minus 6, 0. This is the x in a set. Do you follow me?
Yes.
Okay. And what do you think about horizontal asymptote? It's the same thing. Remember, regardless, well, but it's same thing, but completely different. Because remember, horizontal is when the x approaches to positive infinity, or when the x approaches to negative infinity. Okay, the habit that we have in the rational function is that they are perfect coincidence in between this behavior. And this is a classic that we have horizontal asymptote, and we have a curve, suppose like that. In that direction is the same. However, in the exponential, no, it's not the same end behavior in positive infinity and negative infinity. Why no? Because this exponential, I suppose, can come from of the decay, look, decay exponential, and decay is something like that. So I know, okay, when you move into x to the positive infinity, it's going to zero, that part disappear. Let me explain it. However, when you go in this direction to the negative infinity, oh, that part is increasing, it's infinity. Infinity minus 4 is obvious infinity, because infinity wing is dominant. Now, but I don't care. The important for me is the end behavior in only one direction. No? The end behavior is when they go to the negative infinity is infinity. Okay, y is infinity, look at y is infinity. However, when you go to, no, I make a mistake. This is this. When the y is infinity positive, look at that. Negative infinity is y positive infinity. However, when it's positive infinity, y approaches to zero. And when the y approaches to zero in the exponential without transformation, in our example, approaches to negative 4. And negative 4, again, I intentionally did that, is our horizontal asymptote. Do you understand this or no?
Yes.
Sure? Wow.
Yeah.
Impressive. Okay. So let's move on to the graphic and verify everything that we computed in the piece of paper. Let's try. Try. Let's move. Okay, example 4. Ooh, look at that. Example 4. Do you see decimals?
Yes.
So now remember, we determined the x-intercept. It was negative 6,0. Okay, let me make a zoom to see the picture, big picture of this exponential case. It's different to the classical exponential, no? Because we have transformation. We have how many transformations? When I see 3 transformations, we are doing according to the order of operation. We are doing the horizontal shift 4 units to the left. We are doing reflection because remember that the base is 1/2, que is equivalent to say 2 to the negative 1. This is the reason that this exponential is decay. And finally, minus 4 gets vertical shift down. Okay, so now the important information that we obtained in the piece of paper was x-intercept minus 6,0 and y-intercept was 0, minus 63 over 16. Okay, in the calculator I compute that it was 3.9375. Oh, it's close to negative 4. Very close, but no. Let me make it zoom to see more clear. Very close. You see that or no?
Yes.
Fantastic, eh? Okay, so in the time that we have, it's not too much. I want to practice. I suppose we don't finish. But I want to practice a little bit solution for the exponential equation because I suppose it's important. It's important to do the graphic. It's important also in the word problems. In the word problem, you face exponential equations, and you need to will be able to solve any exponential equation. I classify like easy and complicated, no, but this is easy. Do you see the whiteboard?
Yes.
Okay, so we have two kinds of the exponential equation. Easy, and complicated. The easy is when you will be able to manipulate both sides. That basically we are doing now, guys, exponential equation in detail. And you help me. Exponential equations. We practice. Of course, we practice the easy today. Okay. Example 1, piece of cake, is 2 raised to the 3 minus x equal. Solve that. Solve. Solve means find the value of the x satisfy this. Okay, so you can do by inspection, but not necessarily. You manipulate. You try to find the famous common base. Sometimes it's impossible, but sometimes yes. In this case, yes, because 2 is 2. 2 to the 1, and 8 is 2 to the third power. Clear? So you replace 2 raised to the 3 minus x is equal to the third power. Wow, 2 exponential, same base. Some people lie, I don't lie, cancel out the base. It's not technically polite doing that. The true statement is if 2 exponential is equal and the base is the same, that imply okay, 3 minus x is equal to 3, no? Therefore, x is equal. And this is solution. And by the way, always the exponential equation has solution. Always. Always. Because exponential function is nice. The domain is all real number. We study another function que no. But so far, any solution that we are doing well using this idea is possible. Never is extraneous. Never you need to mandatory substitution in the original to verification. No. Never. Example 2. 5 raised to the 2x plus 1 equal 25. What should I do? Who help me? Who there? My question always is there a common base? Help me to simplification this equation or no? A ver. But I have enough laptop. I don't see very well the chat, sorry. All right, repeat again. In the chat or activate the microphone. What is the base case common? F5, Jenny Rodriguez say F5, professor. F5 because 5 to the 1 and 25, F5 square. Okay. So you replace 5 raised to the 2x plus 1 is equal 5 raised to the second power. If we have 2 exponential and the base is the same, it's because the exponent is the same. And you convert it to the linear equation, super easy, elementary, and you solve this. 2x equal to minus 1 is 1 divided by 2. It's obvious that the answer is 1/2. No. Okay, cool, right? Let me complicate a little bit. Not too much, but today not too much. Today is easy day. Tomorrow, no, Wednesday is complicated. Suppose one more example. 27, example 3, no? 27 raised to the 4x is equal 9 raised to the x plus 2. Okay, it's doing. This is the last one, I promise. What is the common base? Can you suggest me? 3, 9. Jenny say 9. I don't think so, Jenny. Es what? It's 3. Gladys say it's 3. Okay, let me analyze both. I know that there are relationship between 27 and 9. 27 is 3 times 9. But what about 9? 9 is 9. So you know that it's incomplete. However, if you use 3 like a common base, 27 is 3 to the third power, and 9 is 3 to the second power. 3 to the second power. 3 to the second power. Okay? Definitely 9 doesn't work. It's 3. So you replace 27 is 3 to the third power, raised to the 4x, and 9 is 3 to the second power, raised to the x plus 2. You just replace. No 27 anymore, no 9 anymore. Using base 3, common base, no problem. Now you apply the rule of the exponent. When you have different level, multiplication is 3 to the 12x equal 3 to the 2 times. Be careful with the multiplication because you multiply actually 2 times this expression. To indicate this idea, you put a parenthesis. You omit the parenthesis wrong. Okay, entonces if, one more time, you have two exponential and the base is the same, it's because the exponent is the same. My equation is reduce it like that. And now the recipe is okay. Linear equation, well, x is equal to x plus 4, well, x minus 2x equal 4, 10x equal 4 divided by 10 both sides. X is equal, continue here, 4 over 10, but you can reduce it. Remember, in my test, maybe you leave it like that, no problem. However, Alex picky. Remember, Alex is a robot. Alex don't understand very well this answer because you can reduce and lower. You see that 4 and 10 are even numbers. So you divide by 2, 2/5. And this is my beautiful finals. Clear? Okay,
Yeah.
guys. Okay, so I propose stop. We continue Wednesday with the solution of this exponential. I put a more complicated example. Entonces, I open the door to the new function can help me to continue solving when you have no common base. So when you have no common base, when it's impossible, suppose que this example, 2 to the x equal 3. What is the common base between 2 and 3? No common base. So no solution? Yes. Entonces, pero to discover the solution, we need to study new thing. Okay? Now Wednesday, I promise. Okay? Entonces, have a nice day, guys. I am leaving because I have another class. Bye-bye. Don't forget to submit today the test. Tomorrow I will grade.